January 28, 1986. Cape Canaveral, Florida. The air temperature at dawn was 36 degrees Fahrenheit, the coldest launch day in the history of the American space program. 73 seconds later, Space Shuttle Challenger would tear itself apart in the sky, live in front of millions of schoolchildren, watching a teacher become the first civilian in space. This is not a story about a rocket exploding. This is a story about a piece of rubber, 4 inches wide, that engineers had been warning about for 9 years. So how does a warning that's specific, repeated for almost a decade, get ignored completely on the one morning it mattered most? To answer that, we have to go back to a decision made 10 years before anyone died. To understand what killed Challenger, you first need to understand a compromise made a decade earlier, one baked into the very architecture of the space shuttle. NASA's budget in the 1970s was a fraction of what it had been during Apollo. So when they designed the shuttle's giant solid rocket boosters, the 2 white rockets strapped to the sides of the orange fuel tank, they made a decision that seemed purely economical. Build them in segments. Instead of casting one enormous, seamless rocket motor, the booster would be manufactured in 4 separate steel cylinders in Utah, then shipped by rail to Florida and stacked together like a tower of steel drums. It was cheaper, it was easier to transport, and it introduced a problem that didn't exist in a one-piece design. Joints. Between each segment sat a field joint, a place where 2 curved steel walls met, sealed by 2 rubber O-rings stacked one behind the other. These rings weren't decorative. Their job was to hold back 900 pounds per square inch of superheated gas at nearly 5,800 degrees Fahrenheit, screaming to escape. The engineer who designed the sealing system, at contractor Morton Thiokol, had one job for that rubber: seal instantly, seal completely, and never ever let combustion gas find a path outward. Here's the part that sounds impossible in hindsight. The O-rings were never supposed to move. In the original design, the joint was meant to stay rigid under pressure, with the rubber sitting passively in its groove. But real-world testing revealed something the drawings hadn't shown. The instant the solid fuel ignited, the immense internal pressure caused the steel case to balloon outward, a phenomenon engineers called joint rotation. The 2 segments flexed apart from each other by a fraction of an inch right at the seam. That fraction of an inch was the problem. For the O-ring to do its job, it had to react to that gap in real time, swelling instantly to reseal the widening joint before hot gas could blow through. This depended entirely on the rubber's resiliency, its ability to spring back to shape under pressure. And resiliency, as it turns out, is a function of temperature. Rubber that is warm is elastic, soft, responsive, forgiving. Rubber that is cold becomes stiff, almost glass-like. It stops springing back. It just sits there. So what happens when a rocket built for Florida heat suddenly has to fly on the coldest morning in its program's history? Engineers at Thiokol had actually measured this. Internal tests showed that at 75 degrees Fahrenheit, an O-ring could reseal a gap in about 1/3 of a second. At 30 degrees, that same ring took over 10 times longer to respond, and sometimes it simply failed to seal at all. This was not a secret. This was documented, tested, and known years before the accident. The night before launch, temperatures at the pad were forecast to fall as low as 22 degrees Fahrenheit. Engineer Roger Boisjoel and his colleagues at Thiokol looked at that number and felt something close to dread. They requested an emergency teleconference with NASA the night before launch, an almost unheard-of act of resistance in an agency built around schedules. Boisjoel presented data from a previous cold-weather launch, in January 1985, where post-flight inspection had found the worst O-ring erosion and blow-by damage in the program's history, on a launch that had occurred at 53 degrees. Now they were being asked to launch at temperatures more than 30 degrees colder than that. Thiokol's engineers formally recommended do not launch below 53 degrees. What happened next has become one of the most studied moments in engineering ethics. NASA managers on the call pushed back hard, frustrated by what they saw as a last-minute, poorly substantiated objection. One manager reportedly told Thiokol to take off its engineering hat and put on its management hat. Under pressure, and without new technical data to strengthen their case, Thiokol's own management overruled their engineers and reversed the recommendation. The launch was approved. So what does it actually look like when a known, documented risk collides with a countdown clock that nobody wants to stop? The next morning, cameras captured ice hanging from the launch structure. At ignition, sensors and later frame-by-frame photo analysis would show a small puff of dark smoke escaping from the aft field joint of the right booster, the exact O-ring the engineers had warned about, failing to seal exactly as their data had predicted. For a moment, it appeared the joint had resealed itself, as a layer of aluminum oxide from the burning propellant temporarily plugged the breach. But 58 seconds into flight, the shuttle encountered wind shear. The vehicle flexed. That temporary oxide plug cracked open. A thin, flickering flame emerged from the joint, invisible against the bright Florida sky in the original broadcast, but captured by tracking cameras. Within seconds, it became a blowtorch, burning through the strut connecting the booster to the external fuel tank, and then through the tank's wall itself. At 73 seconds, the external tank ruptured. The escaping propellant combined with the shuttle's own momentum tore the vehicle apart in an aerodynamic breakup, not, contrary to popular memory, a single explosion. The crew cabin, structurally intact, continued upward before falling 9 miles into the Atlantic Ocean. All 7 crew members were lost, including Krista McAuliffe, the schoolteacher millions of children had tuned in to watch. The Rogers Commission, formed to investigate the disaster, found something even more damning than a design flaw. It found an organization where warnings existed in writing for 9 years and were repeatedly managed away rather than resolved. Physicist Richard Feynman, appointed to the commission, produced its most famous moment. During a live televised hearing, he took a piece of the O-ring material, clamped it in a C-clamp, and dropped it into a glass of ice water. When he removed it and released the clamp, the rubber didn't spring back. It stayed compressed. In front of the cameras, he demonstrated in 30 seconds what internal memos had failed to communicate for nearly a decade. Cold rubber doesn't seal. NASA redesigned the joint with a third seal and heaters to keep the rings above a safe temperature. But the deeper legacy of Challenger wasn't a hardware fix. It was a warning about how organizations behave under schedule pressure. The data that could have grounded the shuttle that morning already existed. The people who understood the risk had already spoken. The failure wasn't a lack of knowledge. It was a system where inconvenient knowledge lost to convenient deadlines. 17 years later, in 2003, a strikingly similar dynamic, known risk dismissed by management under schedule pressure, would destroy the shuttle Columbia and kill 7 more astronauts. Some engineering disasters happen because no one saw it coming. Challenger is far more disturbing than that. Challenger happened because someone did, and said so, in writing, the night before.